Good morning, everyone. This paper comes from some work that two PhD candidates did during a research stay with my group in Milano. The names are, there are the two first authors for this paper, so Filipe, Marques, and Hugo Magalhães. They're coming from two different universities in Portugal, IST Lisbon and the University of Minho. So, where should I point? Should I point? Sorry. Okay, I was pushing the wrong button. Okay, this is a summary for my presentation, short introduction. Then I will introduce what we mean by the Kalker book of tables for non-Hertz contact. And then the focus in this paper is on the trade-off between accuracy and size for the lookup table. So I will present some results about an assessment of the accuracy for the lookup table, and based on that, proposal at number 4 for the generation of an enhanced table, which in this case means a table having a similar accuracy with the smaller size, and then some concluding remarks. So first of all, an introduction. And the motivation is when we are interested in using and developing and using a contact model in the context of rail vehicle dynamics simulation and simulation of train track interaction, then most probably we are not interested into going into the fine details of the distribution of normal and tangential stresses in the contact patch. We are rather interested in a good description for the total forces and spin moment that arise from the wheel rail contact condition. And then we have different alternatives at hand, all representing in some way a trade-off between accuracy and the computational effort involved with the calculation. One is, of course, using FastSim. That works fine, but as was shown by Sebastian Stickel yesterday, may sometimes be not so much accurate. It is best suited for Hertz contact patches, although it may work also with non-Hertz contact patches. Another alternative is to use heuristic formulae like Chen-Edrick-Elkins or Pollack or other similar ones. They are normally defined for elliptic contacts, so the generalization to non-elliptic is normally not so straightforward and may imply some inaccuracy, although they are very much efficient. And a third alternative is to use a book of tables, which means you invest some initial computation time with computing the relationship between creep edges and creep forces for some selected conditions and for some selected shapes of the contact patch. And then during the simulation, you just interpolate this contact table, which can be a good way to obtain a good accuracy with yet having a very small computational effort involved. Where is the problem? If you stick to elliptic contact patches, then this is quite simple. If you go into non-elliptic, you need to find, you need to add additional dimensions in your contact table to consider the non-elliptical shape of the contact patch, which means the size of the contact table you're building becomes greater, and you may have problems with the time required to produce the contact table, and especially with the storage and interpolation of that table. So the objective of this work is to propose an enhanced lookup table with an optimized size to accuracy ratio, which could be done in two ways, either decreasing the size and preserving the accuracy, that's the focus of my presentation today, or preserving the size and improve the accuracy. Let me first describe how this contact table approach can be done for non-Hertz contact patches. So that's some previous work we did in collaboration with Professor Piotrowski in Warsaw, which originated what we call the Kalker book of tables for non-Hertz contact. This has been published already. It's based on a simple approximation of a non-Hertz contact. It's called SDEC, simple double elliptic contact. It is made up of two half ellipses, one in the negative y values of y and one in the positive values of y, so that some, of course, just some of the possible non-Hertzian shapes can be well reproduced. And this requires, compared to the elliptic contact patch, one additional parameter, which is this y0, which can be turned into a non-dimensional shape factor psi, in addition to the usual A over B semi-ellipse ratio, which is typical for elliptic contacts. And then if you want to build a contact table out of this, besides these two geometry parameters, you have some parameters for the creepages and spin creepage, and there we use a non-dimensionalized longitudinal and lateral creepages and non-dimensional spin creepage, which we then turn into a magnitude for the non-dimensional creepage and angle for the non-dimensional creepage. So we have overall 5 parameters in our table, 2 for the shape, G, psi, 3 for the creepages, C for the spin, alpha and nu for the linear creepages. And the outputs for this are the non-dimensional longitudinal lateral forces and non-dimensional spin moment. And in order to compute the, let me call it the edges of the table, the tabulated values, we use contact software, which is, of course, the one providing the best accuracy among the methods currently used in contact mechanics. This is the original setup for the contact table. That was built based on, let me say, engineering evaluation. So the number and values of the different parameters tabulated, input parameters for which tabulated values were computed, were chosen based on practical evaluation. And this results in a number of points in the table which is in the order of 100,000. So quite not so small. We wanted to perform an assessment of the accuracy for this. So first of all, we performed the sensitivity analysis. We picked up a small number of points which were randomly selected according to late in a hypercube sampling. And then we changed one at a time the different values in the table, the different parameters in the table, considering a refined mesh of 100 points. And I will show you some selected results for these more results you find in the paper. But it's just like to show how the values for the Fx, Fy, and M forces and moments change with some of the tabulated parameters, like in this case with the shape factor for the ellipse A over B. And you see there is a quite strong nonlinear effect of this parameter, which is sometimes looking like a logarithmic trend, and I will come back on this later on. And also the magnitude of the non-dimensional creepage is very much affecting, especially in the low values, whereas in the high values we see a much smaller effect. And then we wanted to quantitatively assess the accuracy. So we compared the result of the interpolation of the lookup table in those points which you see here shown in blue, the centers of hypercells. So this is shown in 3D because, of course, it's the only way I can visualize it, but it is done actually in 5 dimensions, where the black dots are the corners, the interpolated values, so the exact values in the table, and this blue point is the interpolated table, which is the interpolated point, which is assumed to be the point which is farthest from the interpolated, so the one where the lowest accuracy is expected for the interpolation. And we compared the interpolated value to the value directly evaluated at this point with contact. And there you see the effect. These are non-dimensional forces, so the maximum value is 1. So you see that at some, normally the maximum error is quite small, especially for the longitudinal and lateral force, but at some points the error can be quite significant, like in the range of 0.2 or higher for the non-dimensional spin. And then we wanted to know a little bit more how this was happening. So we tried to change one parameter at a time, which means taking the midpoint in the edges of the hypercubes. I need to run a little bit fast on this because I'm getting close to the end of my presentation time. But here you see the effect, and this is, for instance, for the non-dimensional spin, and this one is for the ellipse shape factor G, and so on. So you see that sometimes we have quite significant effect of these variables, suggesting that we probably need some better interpolation here, like having more points here in the book of tables. Whereas in other cases, like the magnitude of the non-dimensional creepage, this is much less critical. So, and this is, sorry, the previous one was for the maximum error, and this is for the average error overall edges in the cells. So out of this, we obtained some directions in order to generate an enhanced Kalker book table for non-Hertz contact. And as I said, this was directed so far towards having a table with a smaller size. So here you see the values for the new lookup table. Unfortunately, it's not reported the old ones, but there is one value less for the A over B ratio. There are less values for the shape factor representing the non-ellipticity of the contact, because this was shown to be not so much affecting the interpolation. Same number of values for the direction of the non-dimensional creepage. Some decreased the number of values for the magnitude of the non-dimensional creepage, because we could see that, especially for large values of this parameter, the interpolation was not was very accurate and did not cause any problem, and one value less for the interpolated values of the non-dimensional spin creepage, resulting in a new size of the table, which is 24,000 compared to 113,000. So it may mean that these changes are minor, but in the end, we ended up with a final size of the table which is more or less 1/5 of the original one, so a considerable reduction in terms of the size and of the time required for interpolation and so on. And when we play the same exercise with assessing the error which is reached, then we got more or less the same maximum error at the edges. Of course, the error on the magnitude is a little bit higher, but still comparable to the error we get in the other dimensions of the table. And this is for the mean errors, which also are not so much affected. So in conclusion, a similar level of accuracy of maximum and mean error for a much smaller size of the table. So I can come to my conclusions. And in this work, it was presented an improved book of tables for non-Hertzian calculations of creep forces and moments. This was supported by a sensitivity analysis on the effect of different parameters. We were successful in reducing the size of the table by a ratio which is nearly 5, with a similar accuracy as the original one. And next step will be to reintroduce an increase in the size to obtain a better accuracy. Thank you very much for your attention.
Okay, thank you.